to the broiling heat of Earth's closest neighbor, radical weather is the norm in the solar system. We do have our own extremes here on Earth, but they pale in comparison to the fastest, dustiest, wettest, and most brutal alien storms. On Earth, the sun drives our weather, and sometimes drives it wild. When hot and cold collide in the atmosphere, watch out. This is true locally and globally. But storms on other planets are bigger, badder, and stranger than their counterparts on Earth. Why is that? Because of the sun? If not, what else fuels their fury? The basic laws of nature, the rules of the game, are pretty much the same wherever you go in the solar system. But every planet has its own way of playing the game. Right now on Mars, the entire planet is being covered in dust. This global dust storm blocks 99% of the sun's rays from reaching the planet's surface. It's actually a system of smaller but still massive storms churning dust high into the atmosphere. Once it starts, it takes months for Martian skies to clear.
Mars is just the most dramatic weather in the solar system in some senses. It's very rare in the solar system you get a weather event that can take out the whole planet.
So if the basic rules of hot and cold are the same on Mars, why is the weather so different from Earth? For one thing, Mars is half the size of Earth. It's also 50% further from the sun, so it's much colder. The average temperature on Mars is minus 80 degrees. That's almost 130 degrees colder than Earth. And the atmosphere is extremely thin and composed mostly of carbon dioxide. But perhaps the most important difference is this: Mars is a global desert.
What would Earth be like without water? Well, it'd probably have a lot of dust.
There's no liquid water at the surface of Mars, and there's very little water in the atmosphere, and so there's nothing to sort of keep the dust down.
On Earth, dust storms are localized and short-lived.
The reason for that difference in scale is that the storms are generating their own weather on Mars, whereas on the Earth, they're slave to the weather that's going on around them.
In other words, on Earth, the global weather system creates dust storms. On Mars, the storms create a global weather system. Astronomers have always been able to see big Martian dust storms easily with Earth-based telescopes. But what they couldn't see was what caused them. That would require a trip to Mars itself. In 2003, NASA landed 2 rovers called Spirit and Opportunity on the Martian surface. Their mission? To learn more about the geology of the red planet. NASA engineers always assumed that as these 2 vehicles roamed the Martian surface, dust would build up on their solar panels.
If you have a lot of dust that's falling down out of the atmosphere and coating the panels, pretty soon you're not getting much sun to the silicon. And in fact, we thought that that was what was going to kill the rover Spirit and Opportunity.
Only it never happened. The rovers didn't die as expected. As dust built up on the panels, somehow something would clean them off. But how could this be? NASA engineers were baffled until the rovers themselves saw the culprit. Martian dust devils.
It turns out that dust devils were sort of our white knight. They came along and cleaned off the solar panels just at the time we were expecting to start having some problems.
There are beautiful photos that actually show dust devils moving across the Martian atmosphere and ghostly soldiers moving out there in the distance.
A dust devil is really an extreme form of rising hot air or convection.
And that hot air wants to go up, and it comes up just like, water going down a drain. Well, this is air that just spirals up into the colder parts of the atmosphere.
Whenever warmer air, which is less dense, rises up through cooler air, which is more dense, it rotates as it swirls upwards. Convection can be very powerful, strong enough to lift things up. On Earth, it lifts moisture, and that's how thunderstorms form. But on Mars, there is no moisture, so it lifts dry, dark dust and creates giant dust storms instead. Once airborne, Martian dust clouds absorb sunlight and heat the atmosphere. This supercharges the convection, lifting still more dust.
That produces more winds, which bring up more dust, and these things can spread up to thousands of miles across, or even, in some cases, they can envelop the entire planet.
And because the Martian atmosphere is so thin, it doesn't take much to get this cycle going.
You get a lot more difference between the surface temperature and the air temperature, and so the convection on Mars is very much more vigorous.
As a rule, Earth doesn't get the temperature extremes that Mars does. But sometimes, here and there in the deserts of Earth, convection can be very Martian-like. And we get dust devils, too. But at Arizona State University, Lynn Necrace makes dust devils to order in a lab to study them up close. He uses a vortex generator and substitutes lighter, dry ice for dust. What he creates is not an exact replica of how real dust devils form, but good enough to see how they pick up dust and debris.
Natural dust devils usually form from the bottom up, as opposed to tornadoes, which form from top down. So what happens when we turn this on, we have the airflow starting, and as the airflow starts to rotate from the fans down to the floor, we actually end up having the vortex form.
In other words, the vortex generator, basically a huge vacuum cleaner, imitates the swirling action of convection.
You can see here there's a wider base where larger particles of the dry ice are being swept up and gets wrapped up and tightens as it expands upward. The center of the core is where the majority of the lifting would occur.
Martian dust devils have been helpful, keeping the rovers clean. But could they actually be making a mess of the rest of the planet? Some scientists think there are so many at any one time, and they lift so much dust into the atmosphere, that together they trigger these much larger dust storms.
It starts wind patterns, and the air's warmer over here, and it's colder over here, and the air starts moving around. Pretty soon you're spreading dust over the whole planet.
And we found measurements that indicate there's up to maybe 200 dust devils per square mile per day during some parts of the summer.
And they can range from a couple of 100 feet tall to devils that stretch 6 or 7 miles high.
You can get just towering monsters of dust devils that we would never see on the Earth. The kind of maximum size dust devils you see on Mars are more like tornadoes on the Earth, where they're going up almost 10 kilometers. So these things are just real monster systems.
Back at Arizona State University, scientists blow crushed walnut shells as silicate particles in the Planetary geology wind tunnel to replicate dust and wind conditions on Mars.
If we can understand and sort of replicate what's going on, then we can, in a sense, understand how the Martian surface has been changing and continues to change as time goes on.
Oddly enough, their studies reveal that it's easier for winds to loft larger sand particles into the air than smaller dust particles.
This is because there's cohesional forces and static forces between the very small, fine dust grains. We imaged the rover deck and actually found that sand seemed to have bounced onto the solar panels, and we can see the skip marks across the surface. Now, this is interesting because we don't usually see sand typically reach that high.
Dust devils on Earth never have the punch to produce that kind of chaos here. Lucky for us. But what would happen to Earth if a giant Martian-style dust storm did overtake us?
If you had dust storms of Martian size on the Earth, you would find your city being enveloped in an orange-tan haze.
Air quality plunges as the storm churns. Dust blots out the sun, shutting down photosynthesis. No plants, no food. Temperatures would plummet. 65 million years ago, an asteroid may have struck the Earth, creating these same conditions, wiping out the dinosaurs.
It's not going to happen on the Earth, though, because there's going to be rainfall and moisture condensing on the dust grains and so forth and dropping them out of the atmosphere. So it's very hard for something like that to spread in the climate conditions that we have on Earth.
Forecasting Martian weather may someday be just as important as forecasting the weather on Earth. If we ever want to send a manned mission there,
The word environment no longer really applies just to the meadow next door and the little stream down at the end of town. It's the whole inner solar system. I mean, that's really our environment now.
the sun's energy bathes all the planets. On Earth, it creates hurricanes. On Mars, planet-wide dust storms. But with almost no solar energy, distant Neptune produces violent and powerful winds. Where do they come from? And just how bad are they? If Neptune's winds were to travel to Earth, these alien storms would literally blow us away. The orbit of Neptune lies 3 billion miles from the Sun, at the outer edge of the solar system. There's a lot we don't know about this big blue planet. Neptune's jet stream winds blast as fast as 1,500 miles an hour in its upper atmosphere. But how? The sun controls the weather on Earth and Mars, but it barely reaches out here. No sunlight means freezing temperatures, an average of minus 392 degrees Fahrenheit. So if there's no sun and no heat, where do these incredible winds come from?
One of the interesting puzzles is that as you go further out in the solar system, you get further from the sun, the winds don't go down. You still get very strong winds.
The energy for Neptune's winds must come from somewhere, and scientists are working to figure it out.
Neptune's energy is certainly not going to be powered by solar radiation. In fact, the energy we detect coming out from the planet in the infrared as heat is 2.5 times the energy coming in from the sun.
So the planet is creating its own heat, not from its core, which is made of rock and ice, but wrapped around this icy center is a mantle of ammonia, methane, and water, all being squeezed by enormous pressure and generating tons of heat. So while Neptune is frigid on the outside, on the inside it's giving off a lot of heat. This heat may help generate Neptune's winds, but they're still too strong to come from the mantle alone. Something else is pushing them faster and faster. Earth has a hot core too, and it's a lot closer to the sun. So why don't we have winds like Neptune? For one thing, our oceans store and release energy, and that helps generate our weather.
That adds energy in places, takes it out in others, in a very complicated system.
This complicated system produces a lot of wind. And just where are Earth's fastest winds found? Surprisingly, not over the ocean. They blow instead over the top of a fairly modestly sized mountain. New Hampshire's Mount Washington.
The highest winds ever observed by human beings were right here on Mount Washington at 231 miles an hour on April 12th in 1934.
Mount Washington Observatory, a private, non-profit scientific institution, is responsible for tracking the weather and climate atop the 6,288-foot tall mountain. This remote weather station, accessible only by snow tractor in the winter, has kept daily records for the last 76 years.
It's definitely one of the most extreme locations on the planet. We regularly see in the wintertime winds exceeding 100 miles per hour every few days.
Nowhere near as ferocious as Neptune, yet still pretty strong. But why does this mountain, 1/5 the size of Everest, produce such fierce gusts?
We're at a place where we have winds converging from various directions, coming from the Ohio River Valley, coming down from the St. Lawrence River Valley, coming up the eastern seaboard, all converging here in this area on top of Mount Washington.
The elevation change from the valley floor to the summit of Mount Washington is very significant for any mountain range. It's over 4,000 feet, so air is forced to go over the mountaintop and forced to squeeze in there, and is accelerated as it's squeezed over the mountaintop.
And they measure it every hour, on the hour, 24 hours a day, 7 days a week.
It's blowing over 100 out here right now. Ice is forming on the instruments more quickly. It's time to go up and de-ice the instruments, even though it's blowing over 100. We got to do it every hour now.
Ironically, Earth's uneven surface, which channels winds into powerful gusts on Mount Washington, ultimately knocks them down over time. And this is the big difference between weather on Earth and weather on Neptune. Earth has mountains that slow winds down. Neptune is as smooth as a cue ball.
It's not so much a question of you're driving them stronger, because you're not. It's just that there's nothing to slow them down.
Simply put, once Neptune's winds get blowing, there's nothing to get in their way. So what would an average Neptune wind speed of 850 miles an hour do to us here on Earth?
We have parking level winds in the Earth sometimes above 100 miles an hour. We consider that pretty dangerous. So if we sat with 900 mile an hour winds from Neptune on the Earth, we would probably start wiping out everything on the surface and scraping everything off.
Giant Neptune takes wind and transforms it into something extreme and almost unrecognizable. But orbiting just beyond the rings of Saturn is a small moon that does the same thing to rain. This is Titan, where an everyday rain shower would turn Earth into an explosive fireball. It's a cloudy day, and a gentle rainstorm starts. Here on Earth, you'd grab your umbrella and consider it a minor inconvenience. But this isn't Earth, and it's no ordinary rain. You're on Titan, a small moon of Saturn. And in this chemical downpour, you'd need more than an umbrella to protect you. The rules of Earth weather definitely don't apply here. But Earth and Titan are alike in a lot of ways. On Earth, we have a solid surface, a protective atmosphere, and plenty of water. All these things make life on our planet possible. There's really nowhere else quite like Earth anywhere in the solar system. But Titan comes close. Like Earth, it has a solid surface. And that's not all.
Titan has an atmosphere that's, in general, very similar to Earth's. In some ways, it's mainly nitrogen, like Earth's atmosphere. It's rich with organic material, also like Earth's atmosphere.
But similar isn't the same. Here on Earth, our atmosphere has a huge supply of water in it all the time, constantly evaporating and raining back down, like here on the Hawaiian island of Kauai.
Today we're on the slopes of Mount Waialeale, which is the cloud-shrouded mountain behind us. It rains over 40 feet a year here.
Earth's water cycle starts when warm, moist ocean air rises, forming clouds that eventually condense into rain. The rain falls back onto the land, where it eventually drains back into the ocean, starting the cycle again.
When water evaporates, it absorbs solar radiation. When water condenses, it releases all that energy into the atmosphere. And this transfer of heat helps to moderate conditions on Earth.
Earth's water stores as much as 80% of the sun's heat, helping keep our temperatures steady from the equator to the poles. Scientists theorize that Titan might have water or some other liquid that might produce a similar effect. And in 2004, when NASA's Cassini probe visited Saturn, it found some pretty good evidence to support that idea.
If you went to Titan and you were looking at the landscape, you would see something that in some ways would look almost familiar to you. You might see big mountains and valleys that were carved out by running liquids.
In fact, as Cassini flew past hazy Titan, its radar read the surface below. Scientists saw channels cutting across the surface, much like rivers on Earth do, some as long as 900 miles. The first strong evidence of liquid on Titan.
There are large bodies of liquid on the surface of Titan. Nowhere else in the solar system except for the Earth are there any large bodies of liquid.
Could water, the liquid that carves Earth's mountains and valleys, also be carving these features on Titan's surface? Or could it be something else? The problem is that Titan is too far away from the sun. If it was water, it would be frozen solid.
It's about -300 Fahrenheit on Titan, so things behave very differently on Titan than on Earth. Because it's so cold, methane, which is a gas on Earth, is a liquid on Titan.
One mystery solved. But just because methane is a liquid on Titan's surface doesn't mean it's part of a weather cycle like water on Earth. So how do we know that this methane also falls from Titan's sky? That answer is shrouded in mystery, literally.
Titan is completely covered in a thick haze of smog particles, like a very, very bad day in Los Angeles.
Despite the haze, the Cassini probe once again revealed the answer.
We can see the upper clouds, and we can see evidence for rainfall because the clouds drop very precipitously. We hypothesize that we're seeing the effects of rainfall.
Methane rainfall.
We think that Titan has methane monsoons, so we think that sometimes Titan has a lot of rain that is able to carve rivers and leave large fluvial deposits on the surface.
Cassini's radar imaging also revealed large methane seas on Titan's surface.
If you have liquid methane on the surface, in a lake, for example, that methane can evaporate off and become methane gas in the atmosphere. So you have kind of a cycling of methane between liquid phase and gaseous phase and between the surface and the atmosphere that's very similar to the water cycle that occurs on the Earth.
But methane is a flammable gas. So why isn't Titan on fire?
For any combustion, you need two things. You need both a fuel, which methane is, but you also need oxygen. And on Titan, you lack the oxygen. So the whole thing is basically a big fuel canister, but there's no oxygen with which to burn it, and so it's all very stable.
If it were cold enough here on Earth to produce methane rain, the oxygen in our atmosphere would create a worldwide firestorm. Luckily for us, that can't happen. Titan's methane cycle makes it both alien and familiar to us.
To me, Titan is very exciting because all the materials are so different, and yet these processes produce very similar landscapes to what we see on Earth.
Titan proves that where alien weather is concerned, looks can be deceiving. On Jupiter, it's all about size. Drop the great red spot onto our world, and it makes even our worst hurricanes look like a breeze. This is the biggest and oldest storm in the solar system, and Jupiter's most famous feature. It even has its own name, the Great Red Spot.
It's about 2 or 3 times the size of the Earth, which makes it the mother of all storms.
We've known about the Great Red Spot in Jupiter's southern hemisphere for more than 300 years.
When Galileo invented the telescope, within a few tens of years, people had seen the Great Red Spot, and it's still there.
Familiar yet mysterious. Nobody knows how the Great Red Spot formed. But scientists are finally probing below Jupiter's cloud tops to uncover more about this enormous alien storm. The storm is powerful. With wind speeds of 300 miles per hour, it rises miles above the surrounding clouds. On Earth, we have storms that seem similar, though smaller and milder. Hurricanes. Also known as cyclones or typhoons, depending on where they form. They're our most destructive weather systems. But is there more than just a passing resemblance between Earth's cyclones and Jupiter's red spot?
When you look at the Earth from space at a hurricane, it's this big swirling pattern. It's round, it rotates. Jupiter's big storms look big and round and cloudy, and they rotate. But there the similarity ends.
In a hurricane, there is an internal core, which is called the eye of the tropical cyclone, and that's a region of very calm winds and no clouds, and usually has a size of about 10-20 kilometers in diameter. And then away from the eye, there is the eye wall. Those are really cloudy regions with a lot of rain. And as you move outward, there is a whole region of about a couple of 100 kilometers with very, very strong winds and very strong rain.
Hurricanes draw power from heat in our oceans. But Jupiter has no oceans, and the sun isn't close enough to power a storm as big as the Great Red Spot. So where does it get its strength? Part of the answer is Jupiter's size. It's the largest planet in the solar system, almost as big as all the other planets combined. This mass generates a very strong gravitational pull, which in turn creates interior heat that rises to the surface. Another piece of the puzzle may be Jupiter's hypersonic rotation. Despite being much larger than Earth, Jupiter's day lasts only 10 hours. In other words, it spins incredibly fast. Could energy from this dizzying spin feed the Great Red Spot?
The weather is really dominated by this fast spin. There's shearing between different latitudes, and that shearing, plus a lot of heat that comes up from the interior of this very massive object, 290 times the mass of the Earth, leads to very violent storms.
Both Jupiter's and Earth's storms spin around in a familiar spiral shape. On Earth, it's because of an effect called the Coriolis force.
I'm sitting at the North Pole, and I want to throw a ball down to a friend who's in Los Angeles. And so if I threw the ball in that direction, the Earth rotates, and the ball will end up in the middle of the Pacific rather than in Los Angeles. So it's like if the trajectory was deflected to its right. And that's what we call the Coriolis force.
This force spins storms clockwise in our southern hemisphere. But there is a stark difference between Earth and Jupiter. The Great Red Spot is in Jupiter's southern hemisphere, and yet it spins counterclockwise. This is because of some other powerful winds.
It's bounded by jets, which are moving in opposite directions. And so like a cog between two conveyor belts, they're just feeding energy and momentum into the system.
Jupiter's complex jet streams spin the storm into organized chaos. But the greatest difference between Jupiter's red spot and our storms may be Earth's solid surface. Once a hurricane hits land, it comes apart pretty fast.
Where they come over land or over mountains, their behavior is very different from where they form over the oceans, and over warm oceans in particular, where we get hurricanes. And on Jupiter, there's obviously no solid surface.
With no land mass to stop it, the Great Red Spot just keeps on spinning and spinning and spinning. Scientists hope to learn more about our weather by continuing to study the storm.
On Earth, there's a limit to how far ahead you can predict the weather. On Jupiter, we can forecast where the red spot is going to be months in advance. It's practical value to understand what makes weather on Earth so unpredictable, and aspects of the weather on Jupiter are much more predictable.
Unpredictable or not, Earth's weather never gets as violent as on Jupiter. That's lucky for us, because if we shrank the Great Red Spot down to fit on Earth, we'd be in for disaster.
On the Earth, we go up to Category 5 hurricanes, nothing but Category 10 hurricane here. Not much would be left.
Alien storms are vastly different everywhere you go in our solar system. Even our next-door neighbor, Venus. They say we're sister planets. Lucky the resemblance doesn't include weather. Otherwise, we'd get seriously burned. Venus may be our nearest neighbor, but somehow its weather is radically different from ours. The second planet from the Sun is a cross between a toxic waste dump and Death Valley, but even worse.
So it's almost a planetary definition of hell.
The temperature is 900 degrees Fahrenheit. The pressure on the surface is the same as half a mile below the Earth's ocean. And if that's not enough, the upper atmosphere of Venus is choked with sulfuric acid clouds and winds clocked at 250 miles an hour.
To get a comparison for Venus, the best thing to do is climb inside of your oven and crank it up. And then in terms of pressure, you're talking about deep sea diving. It's like nothing. There's nothing comparable on the Earth. It's just a very, very extreme object.
On Venus, there's just no escaping the heat.
If you built up a hot spot on Venus, the massive atmosphere would just carry that heat away and spread it around.
But Venus shines so brightly in the night sky because its thick clouds reflect almost all the sunlight it receives. In fact, some early scientists assumed Venus would have moderate Earth-like temperatures.
When we went by Venus in 1962 with a spacecraft, we thought we would find a surface at 90 degrees Fahrenheit, sort of like Miami, Florida.
We were dead wrong. something else must be at work on Venus. But what? So why doesn't Venus cool off the same way Earth does?
On the Earth, for example, we have sunlight coming in, hitting the surface of the Earth. Earth warms up a little bit, but the oxygen and the nitrogen in the atmosphere don't impede the light, so when it gets released out in the infrared, it goes right through the atmosphere and leaves and goes into space.
But on Venus, the atmosphere is 97% carbon dioxide, giving a whole new meaning to the greenhouse effect.
It becomes very, very hard for the surface to get its energy out.
So Venus really taught us a lesson, that if you have a blanketing gas, a greenhouse gas, it can warm up the atmosphere tremendously.
But why does Venus have so much more CO2 in its atmosphere than Earth? The two have much in common. They're even called sister planets. They're almost the same size, have roughly the same amount of carbon, and billions of years ago, both had lots of water. But eons ago, their paths mysteriously diverged. On Earth, water fostered life.
The Earth has most of its carbon in life forms, in the trees and the animals. But if you took all that carbon that's in the near-surface rocks and burned it up or released it, you would then create an atmosphere very much like Venus.
Venus's close proximity to the sun made it too hot to sustain liquid water. Instead, its water evaporated into the atmosphere, trapping the heat deposited by the sun and creating a runaway greenhouse effect. Once in the atmosphere, the water molecules were exposed to solar ultraviolet rays that broke the molecules apart.
It really wasn't recognized by the scientific community how important the greenhouse effect was prior to going by Venus and seeing this amazing place where it was 900 degrees Fahrenheit, not 90.
It took several doomed missions to Venus to figure it out. Starting in the 1960s, both the United States and the Soviet Union sent unmanned probes past the planet and down to its surface. It didn't take long before Venus crushed and burned them. Then, in 1981, the Soviet lander Venera 13 set a record for survival on the surface of Venus. 2 hours and 7 minutes. It was able to take pictures and samples of the surface before being overcome by the heat.
You're sitting there with this 900 degrees Fahrenheit heat all around you. It's going to get in there and bake you after a while.
Scientists one day hope to send a probe to Venus that can survive its hellish environment, to help us confirm our theory of how this planet went astray. Because if circumstances were just a little different, our sister planet might just be our twin. Remove our atmospheric shield, and you're on the road to hell.
As soon as you're heated up to something like 400 degrees or so, you probably start getting some smoldering smoke, and way before it gets to 900 degrees, the Earth would burst into flames because all the oxygen around.
Once the oceans boiled away, the carbon locked in rocks on the ocean floor would cook, and over millions of years re-enter the atmosphere.
Probably if you came back to the Earth system after this happened, you'd find a planet looking much like Venus.
We're a long ways away from such a drastic change, but it's sobering to look at Earth's sister planet when the sister planet went on a very different track than we did.
So cosmic forces turned Venus into a planetary barbecue. But on this violent, stormy world, time and the elements have produced some of the strongest thunderstorms ever measured. Welcome to Saturn. Lightning cuts the sky. This violent weather system grows bigger than the entire United States as it pummels the atmosphere with the most powerful lightning ever seen. Except this lightning can't be seen, because these bolts are electrifying the skies over Saturn. Despite the raw power of Saturn's lightning, scientists have been unable to see it. partly because Saturn's rings are too bright.
The rings are so bright, if you were on the night side of Saturn, it would be considerably brighter than the Earth under a full moon.
But Saturn also hides its lightning within thick, choking clouds of ammonia.
It's probably 100 kilometers down that the lightning is happening, and that complicates seeing the lightning flashes.
But the lightning is there, and scientists know it because they've heard it. Radio wave detectors on the Cassini orbiter have recorded the sound of Saturn's lightning.
We can hear the static of lightning just as you could with an AM radio going down the highway on Earth.
And this static reveals the power of the lightning that we can't see.
You can measure the energy in those radio waves and compare it with the energy that your radio picks up when there's a thunderstorm around on Earth. And the Saturn ones are big. They're more powerful, maybe 100 times.
And Earth's lightning can help scientists understand how storms work on Saturn. Within Earth's storm clouds, just like in Saturn's, updrafts drive moisture higher, causing ice to form. These ice crystals rub against each other, take on a positive charge, and become attracted to negatively charged water droplets lower in the cloud. This sets the stage for a potentially powerful discharge of energy.
Once you get that charge separation that builds up so intensely that some theorize that it can be as strong as 100 million volts, that the cloud then must release that energy.
On Saturn, the same thing happens on a much larger scale. In fact, the lightning is 100 times stronger than Earth's. That's a staggering 10 billion volts of electricity. Thunderstorms in Saturn's southern hemisphere span thousands of miles and can last as long as a month. But scientists aren't sure what makes Saturn's storms bigger and longer lasting. It could be Saturn's supersaturated atmosphere.
Probably the fact that there's more water in the atmosphere, pound for pound, on Saturn makes the storms bigger.
More water droplets means more friction, which means bigger lightning bolts. But energy emerging from the planet may also contribute to the power in Saturn's thunderstorms.
It turns out that where Lightning Alley is on Saturn is a place where the winds are flowing the slowest. If you go deep down in the atmosphere, you'll see the same winds as you do up high. It's a place where the energy being released deep down below can make it on up to the upper atmosphere without being sheared apart, and it allows storm systems to be organized.
Earth's atmosphere isn't built that way. So, as violent as our storms get, they're nothing compared to the systems on Saturn. Even a run-of-the-mill mega thunderstorm on Saturn would devastate us here.
A Saturn-sized thunderstorm on the Earth would mean a thunderstorm that grows to cover all of North America and presumably has very strong winds and rain. This is something that's unprecedented on the Earth.
Saturn's hyper-violent thunderstorms are proof that our planetary neighbors have weather far more ferocious than ours. But the laws of physics that create Saturn's storms are the same laws that create our own weather. Massive dust storms, unrelenting winds, killer lightning, powerful hurricanes, and searing heat.
Tourism is big business. There's almost nowhere on Earth you can't go. But the ultimate destination may be 100 kilometers above your head. Space tourism visionaries are creating the next generation of holidays that are out of this world. The getaway of the future will be a trip to the stars. The opportunity to rocket far from the Earth. The 21st century spaceman could be you. This could be the ride of your life. The Final Frontier offers the greatest adventure holidays. Check into a luxury billion-star space hotel. Catch a game of football in zero gravity. Or treat your partner to a date with a difference by taking them to dinner, trillions of kilometers from home.
The Wright brothers didn't think there'd be hundreds of people having a meal going to London. I think that in my lifetime you will see resort hotels in orbit.
Stardate 2020. Your dream holiday starts here. Just $4 million buys a seat to fly a couple of 100 kilometers into outer space. This is the Galactic Suite Space Resort. Your room is a super deluxe pod, with zero gravity as standard. And this room comes with the most incredible of views. The resort orbits the Earth every 80 minutes. It's possible to watch not just one spectacular sunset, but 15 every day. And this isn't science fiction. It's about to become science fact. In the Spanish city of Barcelona, a team of space architects are hard at work designing a space hotel fit for the stars. They're backed by a secret investor with $3 billion of cash to splash. And they're already taking reservations.
Never
before has the space been designed for tourists, where their comfort, needs and activities take on a different level of importance. What's important to us is to be amongst the first that can do it.
At his boutique hotel, Xavier plans a 3-bedroom deluxe suite. The hotel will travel around the globe at 30,000 kilometers an hour, 450 kilometers up. Xavier's even planned a holiday wardrobe for the space tourist. Check in and slip on a Velcro spacesuit. And you can attach yourself to a wall like Spider-Man. 38 wealthy wannabe space tourists have already booked their hotel rooms in outer space, even though the plans are still on the drawing board. But across the Atlantic, one man is betting on making your space vacation dreams come true even sooner. Just a few kilometers from the casinos, billionaire hotelier Robert Bigelow is taking the biggest gamble of his life.
I kept it a secret for a long time as to what my real ambitions were, trying to work like a dog and save money and take a lot of risks.
Robert made his fortune in hotels. Now he's set his sights a lot higher. But his plans came as a surprise back at home.
When I told my wife that I was going to do something like this, she said, "You're going to do what?"
Robert's idea is out of this world. He's taking real estate into space, developing a giant space station that gives new meaning to high-rise living. He intends it to be used for different purposes, as a home, an office, or a weekend retreat.
What we're out to do is try to create a safe, affordable environment that's larger and larger for people to do all kinds of things.
Okay, I'm in position, Dave.
Building in space is a costly exercise. The International Space Station cost a whopping $100 billion. Robert needed a design that would be far easier to construct and one that wouldn't break the bank to build. NASA came up with a solution. They were developing a huge, lightweight space habitat that inflates in orbit, making it cheap and easy to launch. But when NASA's research costs spiraled, the project was scrapped. Robert saw his chance and snapped up the plans.
These systems are extremely strong. They're not balloons. The best correlation I can give you would be comparing it to the tire on your car. And it's made up of multiple layers, steel belts, and other kinds of very strong materials. And that's the same way with our architecture.
But would the idea fly? There was only one way to find out. In 2006, Robert launched a prototype, hitching a ride on a Russian rocket.
In my mind, I thought, there's going to be all kinds of things going wrong. We're going to fail.
To everyone's amazement, not only did the station inflate, but it also managed to broadcast extraordinary live footage back to Earth.
Biggest shock was, oh my God, you know, what we're doing is working for real. It can't get any better than this.
Now Robert is building the real thing, a full-sized place in space. The launch party is planned for 2014, and the onboard entertainment promises to be spectacular.
We will also have many cameras on board our spacecraft, and on a large section of wall, see any number of different angles of what's outside, so you could get right up on the moon. Even though you're only in low Earth orbit, you might have the moon right in your face.
With limitless shapes and sizes, inflatable buildings could make almost anything possible in space. Imagine experiencing new sports that can only be played in the zero gravity of space. Join the crowd at the Zero Gravity World Cup in a gigantic orbital space sports stadium.
Come on!
This is the dawn of a new era of space tourism. The sky is no longer the limit. But some have been unable to wait to get their space fix. In 2006, Iranian-American entrepreneur Anousheh Ansari became one of the first space tourists.
I believe that there is something inside us always attracting us to the night skies, maybe because we're made of stardust.
She paid $20 million to take a holiday at the International Space Station and made a video of her adventure.
Just having the opportunity to fly from one end of the station all the way to the other, it was great. And I tried to go really fast and show off that, you know, I'm made to be in space. I'm made to be an astronaut.
Everything on board was pretty relaxed, especially in the dining room.
It's the only place that you're allowed to play with your food. Any simple task that you do on a daily basis, you know, brushing your teeth, drinking water, just eating can be fun.
And in space, there's not much space. But this is a room with a view.
This is my sleeping bag right here, right by the best view from the world. And I can see the clouds, the Earth rotating by. I see the curvature right there. That was actually my favorite time to just, you know, look at the night skies. I felt like, you know, I could live in space forever.
Anusha's trip cost her a cool $2 million a night. But there's good news for the rest of us. In your lifetime, you could be taking your own, more luxurious, affordable space adventure.
10, 9, 8, go for main engine start. 6, 5, 4.
One thing stands between you and the ultimate holiday in space: gravity.
Space shuttle Atlantis, reaching the crest of its historic.
To overcome it costs a fortune. $500 million per shuttle launch. The rockets use vast amounts of fuel, held in gigantic throwaway tanks. It's clear that for space tourism to take off, some clever thinking was needed. So in 2004, millionaire space enthusiast Anusha Ansari set the world a challenge by funding a $10 million competition to create low-cost spacecraft.
The only thing that can drive innovation is competition, to make access to space faster, safer, easier, and cheaper.
Teams from around the world took up her X Prize challenge. But in Mojave, California, maverick engineer Burt Rutan was ahead of the game. He was already working on a secret spacecraft.
Can you do a dog? A dog?
Burt is an aviation legend. You might say he's light years ahead of the competition.
Okay, I'm going to do a lion. Okay, you ready?
He had already built a plane so lightweight, it flew around the globe on a single tank of fuel. And he smashed altitude records with Proteus, which soared to more than 63,000 feet.
Ready to go?
Now, he's set his sights on sending tourists into space.
Listening to those that have been in space, the way they describe it, it seems life-changing to look down on the planet. And a chance to go there and look at that? Wow.
Just 5 months after the X Prize was announced, Burt Rutan rolled out Spaceship One. It had taken more than 3 years to build. To escape Earth's gravity, Burt used an ingenious design, with not one plane, but two. An aircraft would carry the space plane beneath its fuselage and release it at 50,000 feet to rocket into space. Pilot Brian Binney fired the rocket.
Good work. Good work. Okay.
Holy, that was
He narrowly missed a collision with the mothership.
That's good, though.
350, suggest shutdown. Roger, shutdown.
Within seconds, he had crossed the boundary into space, 100 kilometers above Earth.
Well, it's really quiet up here. I'm going to get the camera out. Roger that.
Billy was able to take a few snaps for the album, from the first privately built spaceship to reach space.
RCSC on. Copy that, Brian. It's moving and it's green. The CTN's a little warm, but looking fine. 3, 2, 1, coming down.
The civilian race for space had been won. But for Bert, this was only the start of his dream.
If I could please invite onto the stage Bert Rutan, the designer of the first private spaceship, Spaceship One. Bert?
I'll tell you something. I have a hell of a lot bigger goal. And you know what that goal is? I absolutely have to develop a manned space tourism system that's at least 100 times safer than anything that's ever flown manned to space, and probably a lot more. I have to do that.
Bert's ambitions are shared by billionaire entrepreneur Sir Richard Branson, and together they have set their sights on helping you reach the stars. Thousands of kilometers away, at his private Caribbean island, Necker, Richard puts his mind to taking tourists into space.
I'm old enough to have seen the moon landing, and I assumed that I one day would go to the moon. But the decades went by, and government-run space agencies were not that interested in getting you or me into space. So, out of frustration, we decided to create a private spaceship company where we could get as many people as possible to be able to experience spaceship travel.
This is Richard's dream, to use Bert Rutan's spaceship technology to take you on the trip of a lifetime. On board a spaceplane, you'll jet 60,000 feet up, to then rocket at 5,000 kilometers an hour, up to outer space. Pop your seatbelt and float in zero gravity. Then, check out the amazing views. You'll coast 104 kilometers above Earth for 6 whole minutes, until it's time to go home.
This spaceship will glide serenely back to Earth, and my guess is that quite a lot of them will be itching to get back up again.
Today, rocketing to space isn't for the faint-hearted. Astronauts must train hard to prepare for launch day. They have to be super fit to handle the extreme force of gravity.
2, 1, 0. Booster ignition and liftoff of Discovery.
But Richard Branson's business banks on just about anyone being able to fly, regardless of age or levels of fitness. Something Dave Clark, who must find future passengers, is all too aware of.
What if we had the spaceships and we had all these people signed up and then nobody was actually physically able to fly?
To find out if the average person could jet into space, the NASA Center in Philadelphia has developed a custom flight simulation.
We've developed a centrifuge program to replicate as almost exactly what's going to happen to your body in your trip into space.
GX now, concentrate on your breathing.
And finding out how most people would react has never been done before.
The data that they have on centrifuge is mostly from the military. These are the most healthy, perfectly proportioned, physical specimens of the population. These are Top Gun pilots, whereas we have people's kids, people, overweight people, older people.
Now talk about your gene training profile.
75 space tourists, including Richard, have volunteered to go for a spin. They are about to discover what 5,000 kilometers an hour feels like.
You got the training, you got the tools, you know what to do. All right, go. You're at Mach 2, climbing at 80,000 feet.
The trainers ratchet up the G's. This is as close as it gets to the real thing.
You're feeling the rush in the heart, you're feeling the pressure on your chest.
Coming up to Mach 3.
The adrenaline is flowing.
Here's your chance to catch your breath.
Thank you very much.
Richard, tell us, what was it like?
It was wonderful. I mean, it's so important to go through that so that when you actually go into space, you can just lie back and enjoy the whole experience and not be worried about, is your body going to cope?
Richard sails through the test. But will the oldest volunteer, scientist Professor James Lovelock? He's 91 years old, and he's hoping he too will be able to fly to outer space. Space tourists will feel the power of G-forces. During takeoff and landing, the heart struggles to pump blood to the brain. But with training, it is possible to avoid the dangers. By squeezing your leg muscles, you can improve blood flow, making for safer spaceflight.
Welcome back to Earth, astronaut. You are now our most senior centrifuge rider. You hold the record. Oh, good.
All 75 wannabe space tourists pass with flying colors, proving it is possible to fly into space, whatever your age or condition.
Did well. Did well, James.
The G-forces are quite brief, and the centrifuge has now shown that really anybody can do this flight. Stephen Hawkins is planning to go into space with us. He'll be able to put up with it. James Lovelock, the environmentalist, he's going to go into space with us.
Now, it's just a case of saving up to buy your ticket for $200,000.
We've got to try to come up with, clever ways of getting that price down and down and down. Every $10,000 we can get it down opens the market up that much more. And I think 50 years from now, hopefully literally hundreds of thousands of people will be able to afford to go into space.
Richard Branson had the vision to turn space into the ultimate tourist destination. Now, all he needed was a spaceship. Back in Mojave, following his X-Prize win, Burt Rutan and his team started engineering his space tourist dream.
What we're doing is important because it's doing something that's never been done.
Burt's prize-winning prototype, Spaceship One, carried just one pilot into space. There's not enough room for space tourists, so Burt scales up his spaceship and creates a version for 6 passengers. And it's built with the sightseer in mind. Each passenger gets a window seat next to an aisle. It's double the size of its predecessor, so it needs a bigger, twin fuselage mothership. But safety is always a top priority.
We can't achieve the level of safety that you do with modern airliners because they've had 7 decades of maturity. However, I do feel that to fly the public, this should not be looked at it as a dangerous adventure.
But modern airliners don't have to re-enter our planet's atmosphere. Anything speeding towards Earth tends to burn up. Bert's determined to ensure his spaceplane will be hundreds of times safer than spaceflight today. So, he has developed a revolutionary way for his spaceship to re-enter the Earth's atmosphere slowly. The spaceplane's wings pivot 65 degrees. Its fuselage flattens into the airstream, creating stable drag, like a shuttlecock. Spaceship Two is so lightweight and the drag so high, it rapidly slows down without heating up. Then, at 70,000 feet above the ground, the wings realign like a glider, and the craft touches smoothly down on the runway.
My solution was to find the very safest way to land a manned spaceship. To me, it was the simplest way of doing a difficult job.
October 2010. It's taken 5 years to develop Spaceship Two. Today, she's leaving the hangar for her maiden voyage. At Mojave Spaceport, there is only one question on everyone's lips. Will she fly? Richard and Bert have gambled their reputations and a small fortune on the odds that she will. They are about to find out.
Standing next to Bert, watching it get higher and higher and higher. Obviously, Bert was understandably extremely nervous. I was nervous for him and for us.
45,000 feet above their heads, it's the moment of truth.
10 seconds. We are armed.
Release.
Clear the plane. Good release.
Okay, it's gone. All good, all good. Beautiful.
Yeehaw!
That's great. Beautiful flight.
She flies perfectly.
We got word back that it was flying absolutely beautifully. It was a tremendous moment. You know, we really are close to the dream becoming a reality.
Beautiful job, Steve.
The final frontier is one step closer. Soon, you could be taking your seat on this spaceship for your unforgettable 6 minutes in space. But for these stargazers, this is only the beginning. If they have their way, you could travel on their spaceship to an orbiting hotel for the ultimate space vacation.
A lot of my life has been about dreams. If you don't dream, you don't make anything. One day you might see a giant V floating around the Earth.
The Wright brothers didn't think there'd be hundreds of people having a meal going to London. I think that in my lifetime you will see resort hotels in orbit.
Staying at a space hotel, you can expect more than 5-star luxury. From here, you can gaze on an entire galaxy.
I think the important thing about being in a space hotel is that you have massive windows, and so you can look out at the universe around you and marvel at it.
And once you've been there, space travel agents will be booking your trip to the next holiday hotspot. Have you ever gazed up at the moon, tracking across the night sky? and wondered what it might be like to visit, to fly over its craters, or take a walk across the lunar landscape. At 400,000 kilometers from Earth, it would take you days to get here. So once you get here, you're going to want to stay around. In Las Vegas, Robert Bigelow thinks he can offer you the perfect place to stay. His inflatable space station could open as the first moon hotel.
What you have is an entire station that's really a potential lunar base. We would use low Earth orbit as the trial place of assembling these craft. And with a few modifications, we can turn these stations into bases.
Once you land here, Hotel Moon will offer the latest in cosmic comfort. This is one resort where they really will have thought of everything, including the breakfast buffet. In the arid desert near Tucson, Arizona, feeding lunar tourists is food for thought.
We're going to go to the moon, or we're going to go to Mars or beyond, and we have to survive. And unless we're going to carry a picnic basket of fresh vegetables and processed foods, which we can't do in the long term, we're going to have to grow our own.
If you're going to enjoy fine dining on the moon, you'll need a space food expert like Dr. Gene Giacomelli. He knows how to grow crops that are out of this world.
I find this very exciting, to be able to use agricultural technologies to grow plants to feed people like we do on Earth, but to bring that to space.
On Earth, our atmosphere filters out dangerous solar radiation that would otherwise wipe out crops, rainforests, and woodlands. But on the moon, there's no protection. For crops to survive, a greenhouse would have to be shielded. Buried underground to protect it from the sun, it could nurture crops with very little help from people.
The lunar greenhouse, in many ways, is a robot. It automatically provides its climate so that the plants grow in the way we want them to grow. It provides the temperature and the light, carbon dioxide, as well as the hydroponic system for nutrients and water.
Gene and his team have already built a prototype lunar greenhouse. On the moon, it would assemble itself, pre-packed with seeds ready to germinate. These plants don't even need soil. They can hang inside plastic envelopes, their roots bathed in nutrient-rich water.
But there it is.
Nice roots, Dr. G.
We're growing tomato, sweet potato, strawberry, and lettuce. And this certainly isn't a full diet, but it does offer the crunchiness of a salad, carbohydrate with sugar, and strawberry as a sweet fruit.
Lunar crops will generate drinking water and convert carbon dioxide into breathable oxygen, giving you not just a taste of home, but keeping you alive in space wherever you go.
The system certainly can be used on Mars and the Moon, but why not beyond? Why not in space stations and intergalactic traveling spaceships, providing food and life support for the space travelers?
Getting to Mars on today's rockets depends on planetary alignment. The flight is only possible every 2 years, and the trip takes 7 months. Once there, you wouldn't be able to set off for home until Earth realigns again, 18 months later. So engineers and scientists have been looking for a much faster way to fly. Houston, Texas. Behind these shops, in a seemingly bland warehouse, a multi-million-dollar experiment is underway that could put Mars on your space trip itinerary. Franklin clocked a record-breaking 7 trips on the space shuttle. As the wheels touched down on his final NASA mission in 2002, his need for speed grew. He needed a faster set of wings.
Right off the bat, we know that we need something entirely different, something that would get us to speeds that are maybe 10 times faster than what we could do today.
Scrapping conventional thinking, Franklin throws away the rulebook and works out what the problem with speed boils down to.
The fundamental issue of rocket propulsion is that you want the exhaust to be very hot, and the hotter the better.
So, Franklin cooks up a revolutionary new rocket engine. It's powered by one of the hottest things known to man, plasma, and it's about to be fired up inside this vacuum chamber. The rocket is powered by hydrogen gas, which when heated turns into pure plasma. Powerful magnets push the plasma through the engine to supercharge the spaceship. Plasma is so powerful, you could jet around 4,000 kilometers in a minute and rocket to Mars at 200,000 kilometers an hour, slashing a 7-month flight to just 39 days, with 2 weeks rest and relaxation when you get there. That's a 100-day return trip compared to 3 years flying today's rocket ships.
All my life, I've dreamed about going to Mars and beyond. Space is like a drug, you know, once you get hooked, you don't want to give it up.
In Los Angeles, science fiction is becoming science fact. NASA scientist Dr. Kevin Grazier advises Hollywood on science fiction. And he thinks what you see on the big screen could be just around the corner.
The days of a few astronauts, cosmonauts, going into space, that's over. In the not-too-distant future, we're going to see you, me, regular people going into space.
Kevin thinks science will let us boldly take a holiday where no man has done so before.
A really far-out propulsion system that NASA has actually looked into is antimatter.
Buckle up for a journey on board your intergalactic space liner powered by antimatter. A look under the bonnet reveals a magnetic chamber that contains antiparticles. They're fed through magnetic rings to collide with their nemesis, matter. In just a nanosecond, billions of explosions create an enormous surge of energy, 10 million times more powerful than today's rockets, with a top speed of just over 1 billion kilometers an hour.
Distances to the planets are puny compared to the distances to the stars and galaxies beyond. If we're going to go to places further than our solar system, we're going to have to speed things up quite a bit. Enter wormholes.
Even flying at light speed to our nearest major galactic neighbor, Andromeda, gives new meaning to long haul. It's a 2.5 million year flight time. So if you're going to cruise beyond the Milky Way, you're going to need a serious shortcut.
The name wormhole comes from an apple. Imagine a worm on the surface of the apple who wants to get to the other side. He can do it one of two ways. He can walk all the way around the outside, or he can chew through the middle. The second is a lot shorter, and that's the basic principle of a wormhole.
If we could bend space-time, we could create a wormhole, a time-saving tunnel that connects two places trillions of kilometers apart. Wormholes might already exist and could become your intergalactic freeways to mind-boggling vacations.
One day you might board your shuttle for Wormhole Express at LAX or Heathrow, take that shuttle to your Starliner, and zap!
Do you fancy a vacation trillions of kilometers from Earth? To holiday in a floating city? To soak up a different sun in a distant galaxy? In the future, we may think nothing of traveling throughout the universe. By having fun in space, tourists could create unimaginable new inventions that would reshape our world. Just as the home computer was initially used for simple gaming, it's now the bedrock of our everyday lives.
The people that will be flying in commercial space flights are allowed to be creative. There's going to be 2 or 3 people that come up with something that's called a breakthrough. And all of a sudden, commercial space travel will look completely justified rather than look at, well, these are just joyrides.
Space tourism could take us all to new places and might ultimately ensure our survival.
Earth is the cradle of humanity, but one shouldn't remain in the cradle forever. Single-planet species don't last. Ask a dinosaur.
Pushing out beyond Earth's orbit will truly become a space species.
I cannot envision all of humanity remaining on this planet. Humanity's destiny is in space.
It's not a matter of if the commercial space industry will take off, but when. It was just over 100 years ago that the Wright brothers flew their first airplane, and now we don't think a thing about jumping in an airplane and flying across the continent or across the largest ocean. Today's commercial space pioneers who are just tickling the edge of low Earth orbit are today's Wright brothers.
We also now know that Saturn is orbited by over 60 natural satellites. The largest of Saturn's satellites is a moon called Titan. It is enveloped in a thick atmosphere, one filled with orange haze. In 2005, a NASA probe penetrated the veil of mystery and sent back the first images of the surface. The terrain looked amazingly familiar. Black lines branched out over the surface. They looked just like rivers. And numerous lakes were discovered. This was the first time any celestial object had been found with liquid on its surface. The more the probe investigated, the more Earth-like Titan seemed to be. It was at this point that scientists began to suspect that life might be present.
Maybe in the seas, more interesting things happen. Maybe you get self-replicating chemical systems, much like those that are the first steps towards living systems that were deep in our own history. So Titan gives us a whole new set of possibilities.
There's the possibility that maybe there is life on Titan that has somehow found a way to make use of all of these building blocks that the atmosphere is making for it.
However, the temperature on Titan is minus 180 degrees Celsius. Could life really exist there?
Well, how do we know it's too cold? Imagine you're living on Titan and you're looking at the Earth. You'd say, oh, there's a liquid, there's organics, there's energy, but it's too hot.
Titan has both an atmosphere and liquids. Could life exist there? This planetary body, very similar to Earth. Saturn's moon, Titan. Imagine the journey from Earth to Titan. If you could travel at the speed of light, you'd pass Mars about 4 minutes into the voyage. At the 30-minute mark or so, you would pass the giant ball of gases known as Jupiter. Then, some 70 minutes after departure, you would finally arrive at Saturn, surrounded by those beautiful rings. Like Jupiter, Saturn is a large, gaseous planet. Finally, you'd reach Titan. With a diameter of 5,000 kilometers, Titan is about 3/4 the size of Mars. It's a moon the size of a planet. Fully cloaked in that orange haze, Titan's true appearance was not known until the 21st century. (1997) saw the launch of the Cassini-Huygens mission. The Cassini orbiter, equipped with cameras and other instruments, and carrying the Huygens probe, was sent to investigate Saturn and its moons, especially Titan. In 2004, 7 years after liftoff, Cassini-Huygens reached the vicinity of Saturn, 1.4 billion kilometers from the Sun. Cassini then proceeded to enter into orbit around the planet and its satellites, and to commence scientific observations. It took this image of Titan. For the first time, Titan's true features began to show from under that thick haze. The day was approaching when we would finally be able to see the surface of Saturn's giant moon. In December 2004, the Huygens probe separated from Cassini and coasted to Titan. The target landing site was near Titan's equator. What that site would be like, no one knew. Titan's atmosphere is 1,000 kilometers thick. The probe entered it. Huygens deployed a parachute and drifted down, jettisoning its heat shield. This image, taken from a height of 152 kilometers, was Huygens' first view of Titan, which was still obstructed by haze. Huygens was shooting still images as it descended. Its microphone also captured the sound of the wind rushing by. This was the first sound recording ever made of an alien environment. These images of Titan's surface were taken by Huygens from 16,000 kilometers up. Black veins, like the branchings of a river, are visible. It does look as though they are flowing to the mouth of a river. Now, from 8,000 meters above Titan, it looks just like the sort of coastline we're used to seeing on Earth. Finally, the landing. This is an image taken by Huygens just after landing. What look like rocks and pebbles strewn about over a flat plain are actually chunks of ice. The surface temperature is minus 180 degrees Celsius. Atmospheric pressure is a little higher than Earth's, 1.5 bars. The horizon seems blurred by mist. This is exactly like some rocky desert landscape on Earth. High above, the Cassini orbiter continued its observations. In the equatorial region where the Huygens probe landed, Cassini discovered a strange pattern. Some sort of regular striping. Further observations found similar striations covering some 20% of Titan's surface. Ralph Lorenz has dedicated himself to investigating this strange striped pattern. He is trying to solve the mystery of Titan's stripes by comparing them to patterns he finds on Earth. This is the Mojave Desert in the western United States. Lorenz believes Titan's stripes are like the peaks and troughs of desert sand dunes. There are indeed real similarities.
It's remarkable somehow that despite the different gravity, the thicker atmosphere, and the different material that the sand is made of, somehow the landscape ends up looking almost exactly the same as many places on Earth. By comparing the shape of the dune and the interaction with the rest of the environment, we can get an understanding of how these structures formed. And for example, different shapes of dunes form in different wind patterns.
So the goal is to solve the mystery of Titan's stripes by investigating terrestrial desert dunes. Lorenz's first step is to send up a kite with a camera for an aerial overview. He's looking for a place that has a striped pattern like Titan's. Next, he mounts a dune buggy equipped with GPS. He wants to measure the heights of dunes and the angles of their slopes. The shapes of sand dunes change by the minute. Lorenz plants a stake with a streamer attached. In fact, he plants a whole line of them along this slope. This will show what sort of wind creates this type of dune. The wind is blowing from screen left, across a gentle slope. Then it swirls around, as if to carve out that slope to the right. So it's become clear that here the wind flows from the milder slope over and down the sharper slope. Lorenz believes that the stripes on Titan are also wind-sculpted sand dunes. A closer look at that image of Titan's stripes shows ridges with milder and sharper slopes, similar to those in the Mojave Desert. So Lorenz conjectures that the wind on Titan must have been blowing from left to right. The winds blowing on Titan's dunes, however, are thought to be weaker than the winds on Earth. The reason for that is that Titan's gravitational force is only 1/7 of Earth's. A relatively small action can produce a big result. So on Titan, effects similar to those seen on Earth are being produced by mild winds.
Titan is still an active world where, geologically speaking, processes are still happening. And the fact that we can see sand dunes, for example, suggests that the winds that move the sand around are still active, that we're seeing a dynamic planet, much like the Earth.
There was another unexpected aspect to those images taken by Huygens. Look closely at those chunks of ice on the ground. They are reminiscent of stones turned over and over by rivers on Earth. Sharp edges are worn down. They're rounded, like pebbles. So there may well be liquid on Titan. This discovery attracted attention and astonishment. Meanwhile, the Cassini orbiter made a surprising discovery of its own. Black spots and blotches were visible near Titan's north pole. Radar observations showed them to be lakes, filled with some liquid. They number in the hundreds, and some of them are huge. This is the first time liquid has been found on the surface of any celestial body other than Earth. The lakes are dotted with islands and fed by rivers. But with a surface temperature of -180 degrees, any water on Titan would have frozen. What liquid could it be in these lakes and rivers? This is it. Liquid methane. On Earth, it's normally a vapor, but at extremely low temperatures, it condenses into a liquid. Methane melts at -182 degrees Celsius. It boils at -161 degrees. In the 20-degree range between those two extremes, it exists in a liquid state. The temperatures on Titan's surface are just right for liquid methane. Methane is composed of 1 carbon atom and 4 hydrogen atoms. It's the simplest hydrocarbon. and it constitutes the bulk of the liquid in Titan's lakes. A portion of the liquid is ethane, another hydrocarbon with similar characteristics. Scientists at the Jet Propulsion Laboratory are trying to determine how Titan's methane lakes were created by conducting experiments here on Earth. Christophe Sautan is an expert on bodies of ice found in the solar system. This device is called the Titan chamber. With internal air pressure at 1.5 bars and a temperature of -180 degrees Celsius, it reproduces Titan's environmental conditions. Inside is placed a disk of ice, standing in for the terrain on Titan. They then release droplets of liquid methane onto the surface of the ice. The methane disappears immediately, absorbed by the ice, like water being swallowed up by a thirsty earth.
So the big surprise, something we did not expect, is that when the methane falls on the ice, well, actually the methane got sucked into the ice. It gets absorbed. It doesn't run on the ice.
However, if methane continues to drip onto the ice, eventually it begins to pool on the surface. This suggests that wherever there are lakes on Titan, the surrounding ice must be saturated with methane. During its landing on Titan, Huygens measured the concentration of methane. That concentration gradually rose the closer the probe got to the surface. Then, the moment it landed, there was a sharp increase. It is thought that this was due to the heat from Huygens vaporizing the methane that permeates the ice. On Titan, liquid methane acts in ways similar to water on Earth. In June 2012, for example, Cassini observed a strange phenomenon near Titan's south pole. An oddly shaped mass seemed to be squirming about in the atmosphere. It was a cloud, swirling. A cloud made up of methane. On Earth, water is recycled as water vapor and rain. One of the factors prompting this is seasonal change. On Titan, the same sort of mechanism seems to be at work. Titan is tilted on its axis, some 26 degrees off vertical. The Earth has a 23.4 degree tilt. It's another point of similarity. Along with its parent planet, Saturn, not shown here, Titan takes 30 Earth years to orbit the Sun. The tilt of its axis gives birth to different seasons. At this location, Titan's northern hemisphere experiences the long days of summer. The northern hemisphere is warmed, producing rising atmospheric currents. Liquid methane on Titan's surface evaporates and is carried southward. Near the South Pole, it is winter. The methane gas is cooled, condensing into a liquid or even solid state. It can form clouds. Like that huge swirling cloud Cassini spotted. When it's winter in the northern hemisphere, the cycle reverses. Now the methane cloud forms near the North Pole. underneath that cloud, methane rain begins to fall. Since methane is more viscous than water, its raindrops are larger, with diameters of about a centimeter. But as Titan's gravity is weaker than Earth's, the droplets fall more slowly, about 1 meter per second, like a soft snow on Earth. They soak the icy ground on Titan and form lakes. Wind blows, rain falls. When people could finally see Titan close up, they were astonished at how much it resembles Earth. In 2007, the Cassini orbiter spotted something truly peculiar on Titan's surface. A land formation some 70 kilometers across, in the shape of a flower. What could it be? Perspective can be gained by combining images taken from two different points of view. A three-dimensional image of the topography emerges. That strange formation turns out to be a rugged mountain featuring a 1,500-meter high peak. There's also a chasm that looks like it might be a volcanic crater. From that, one can infer a formerly active volcano. That volcano has been an object of particular interest to Jonathan Lunine, an expert on Titan's internal structure. He says that the volcano did not spew lava. Rather, it pumped up a mixture of ammonia and water.
One thing to remember is that when water is mixed with ammonia, it can stay liquid down to very low temperatures, down in fact to -100 Celsius. But at that point, within a few degrees of that point, the liquid is actually very viscous. It's almost like basalt. And so if that is what is flowing out on the surface, we would see very thick flows.
Lunine believes that under the ice beneath the volcano, there's an ocean. He came to this conclusion due to changes in Titan's shape. Titan completes its elliptical orbit around Saturn once every 16 days. During that time, it regularly feels the changing effect of Saturn's gravity. In short, it experiences tidal forces. At its farthest point from Saturn, Titan is almost perfectly spherical. But at its closest point, where Saturn's gravitational pull is the strongest, Titan grows fatter. Its diameter alters by as much as 10 meters. Lunine says that Titan can transform so dramatically because internally it is not made entirely of solid rock. Lunine's observations suggest the following picture of Titan's structure. The outer crust of ice is some 50 to 100 kilometers thick. The center is comprised of two types of bedrock. In between the ice and the rock, however, is a layer of liquid water. The bedrock generates heat, says Lunine, permitting the water to remain in a liquid state. This ocean layer is some 300 kilometers deep. Ammonia, present in Titan since its origin, has also dissolved into the water. It is thanks to this ocean layer that Titan can change shape so flexibly.
The interior is warm enough that really only liquid water is a suitable, stable material in that region. So we're pretty sure from the gravity experiment that Titan has a liquid water layer under its surface.
According to Lunine, the tidal forces caused by Saturn in turn stimulate volcanic activity. Tidal forces cause friction along the boundary between the ice and the subsurface ocean. The water heated in this way melts some of the icy crust. It builds up like terrestrial magma and eventually forces its way up above the surface. This ammonia-laden water flows out from Titan's volcanoes like lava. Lunine believes such volcanoes are proof of an underground ocean. Beneath Titan's icy shell, a whole new world lies hidden. Saturn has over 60 moons. Among them are Enceladus, ice-covered like Titan, and Hyperion, pockmarked with craters. Mimas has this huge crater. Those are just a few of Saturn's moons, but they all have practically no atmosphere. Only Titan boasts an atmosphere that extends as far as 1,000 kilometers into space. Actual measurements reveal that this atmosphere is 98% nitrogen. The rest is largely methane. Why is Titan the only one of Saturn's moons with a thick atmosphere? Solving that mystery through experimentation on Earth has been a preoccupation of Yasuhito Sekine. Sekine believes that Titan's atmosphere was generated by an extraordinary mechanism. The mechanism? Collisions with small celestial objects. Sekine is trying to reproduce that effect using a laser. When Titan was first formed, its icy landmass contained about 1% ammonia. So inside a vacuum chamber, a disk of ammonia water ice stands in for the young Titan. The laser beam enters from the left of your screen. It strikes a projectile, which then impacts the ammonia disk. That was the laser shot. Gases released by the impact are measured. One is nitrogen, released by the disintegration of the ammonia. Titan's thick atmosphere contains large amounts of nitrogen. According to Sekine's calculations, based on his experiments, repeated impacts by small celestial objects could have produced just such an atmosphere.
タイタンの地殻中にもともと入っているぐらいのアンモニアの量があれば今の 1.5 気圧の窒素の大気を作ることができるということを明らかにしました。重要な点はですね、大きい天体でないと大気を重力的に持てないということです。なので他の衛星たちは同じように衝突は起きたんですけど、それぞれが小さいがために窒素の大気を持つことができなかったと。
For example, Enceladus, one of Saturn's other moons, is merely 500 kilometers across. That is 1/10 of Titan's diameter. Saturn's other satellites are also small, with weak gravitational fields. So even if they've been similarly impacted, they haven't been able to hold on to any atmosphere. But did Titan in fact experience repeated bombardment by small celestial objects? Hal Levison uses computers to calculate the history of the solar system. He has advanced the revolutionary theory that some 4 billion years ago, the entire solar system was shaken by a massive event. Leveson argues that when the solar system was forming 4.6 billion years ago, Uranus and Neptune were closer to the Sun than they are now. He inputs the location and size of the planets, and also of the small celestial objects that lie further out. Then the simulation begins. At first, the basic situation did not change much. But some 600 million years later, Uranus and Neptune were suddenly flung to the outer realms of the solar system.
Then out, okay? And that caused the giant planets to slowly spread. It was infinitesimal, you wouldn't have noticed it, but the orbits were slowly changing. And that continued until Jupiter and Saturn got to the point where Jupiter was going around the Sun exactly twice. Every time Saturn went around once, and that configuration is what set the whole instability off. Okay, so you went almost overnight from a time when, okay, there was a little bit going on, but not much, to this very violent period where all hell breaks loose.
The smaller celestial objects, shown here in green, had formed a ring at the outer edge of the solar system. But then the gravitational force of Uranus and Neptune violently scattered these objects. The result was that in the period from 4 billion to 3.9 billion years ago, the planets of the solar system encountered a barrage of small celestial objects. During this period, Titan also was hit repeatedly, developing a nitrogen-rich atmosphere. That made it a very special moon.
たった1億年とかそれぐらいの短い期間なんですけど、その間にですね、その 1.5 気圧という膨大な量の大気を作ることができたというふうに考えられます。タイタンっていうのはですね、唯一人類が初めて見つけた生きている天体だというふうに言えると思います。で、地球と同じようにですね、表面で液体が存在して、それが蒸発して雲を作って雨を降らしてというような循環が起きているのはですね、現在の太陽系の中では地球とタイタンだけです。で、その点において40億年前のその出来事というのはタイタンにまさに命を吹き込んだと、生きている天体にしたという意味で非常に画期的な出来事であったというふうに思ってます。
1977 saw the launch of Voyager 1. Its mission? To explore and observe the outer planets, from Jupiter to Neptune. This was its view of Titan. It was a close look, but still the moon was shrouded in a thick orange haze. However, even then, one scientist maintained that the haze held the secret to sparking life below. Bishun Kare has been trying to penetrate the mystery of Titan's haze since the early 1970s. He participated in the Voyager mission. He has focused on the haze as being itself a source of life. Kare introduces a nitrogen-methane mix into a sealed flask to simulate Titan's atmosphere. The flask is fitted with electrodes. Now Kare discharges them. This is meant to reproduce the effect of lightning or other energy surges on Titan's atmosphere. It's about 10 hours since the start of the experiment. A reddish-brown substance has become visible inside the flask. Kare claims that this is the very same substance as the haze enveloping Titan. So what happened inside that glass vessel? First off, the electrical surges split apart the molecules of nitrogen and the methane. Their atoms recombine with carbon and other atoms in all sorts of ways, forming a variety of new organic compounds. analysis showed that some 200 types of organic compounds had been created in this experiment. Organic compounds are the materials out of which our own bodies are made. They are the building blocks of life. It was thanks to Carré's work that Titan came to be considered one of the celestial objects on which life might exist. The Cassini orbiter's close-up observations of Titan have come some 30 years after Carré's experiments. Will they confirm that Titan's hazy atmosphere has in fact given rise to organics? The INMS is a device that measures molecular mass. Cassini has used it to determine the composition of Titan's atmosphere. Cassini's data were streamed back to Earth, where they were analyzed by Hunter Waite and his colleagues. Waite led the team that designed the INMS instrument package carried aboard Cassini. Waite's lab was able to reproduce and confirm Cassini's data by utilizing the same INMS system. They could then analyze accurately whatever molecules or compounds the instrument had detected. The results were astonishing. Rendered in the form of a chart, each of the different molecules identified by Cassini is represented by its own colored area. Various organic substances were created in Titan's atmosphere, ranging from ones with a single carbon atom to more complex ones with 6 or 7 carbon atoms.
When Cassini sent back data, we found out that the upper atmosphere was much more relevant than we ever thought, that most of the chemistry seemed to be going on in the upper atmosphere, that very large molecules were being created in the upper atmosphere, way beyond our expectations. Titan is one of the best organic factories in the solar system.
Bathed in ultraviolet and cosmic rays, Titan's upper atmosphere is continually engaged in converting nitrogen and methane into a rich array of organic compounds. As these compounds collect in the lower atmosphere, they produce Titan's famous orange haze. Finally, they are precipitated with methane rain onto the surface as well. It's been 4 billion years since Titan's atmosphere was formed. During that time, it is estimated the organics settling onto the surface have created a layer dozens of meters thick. The dunes discovered near Titan's equator are thought to be a large deposit of these organics.
Now on Titan, the sand is made, we think, from organic material, and we think that material comes down and gets built up into sand-sized particles that are then accumulated by the wind to form dunes much like these.
Amidst this accumulation of organics on Titan's surface are substances of vital importance to the emergence of life. That finding was made by a young researcher with a specialty in organic chemistry, Sarah Hurst. Hurst has undertaken a minute examination of the organic compounds discovered in Titan's atmosphere. She's written her own computer program to do that. Based on Cassini's observational data, she faithfully simulates the composition of Titan's atmosphere and produces the same organics. Next, she uses her computer program to determine the molecular structure of every compound.
These peaks right here are the masses of the ions in the mass spectrum data, and then it's the number of carbon, nitrogen, oxygen, and hydrogen in each of those peaks. And so then what the code does is it goes through and compares this information to a list that I've given it of all of the amino acids and nucleobases that we're looking at. So here we have, at 136, we have the molecular formula of adenine, which is 5 carbons, that matches. It has 5 nitrogens, it matches. No oxygen, and then 5 hydrogens. So we know from this that we have the molecular formula of adenine in this sample.
Genetic information for all life on Earth is encoded in DNA. Adenine is one of its 4 major components, or nucleobases, and all 4 have been produced in Hurst's experiments. If these nucleobases combine in such a way that they create DNA, then a huge step forward will have been taken towards life itself. With this discovery, speculation mounted that Titan might actually be capable of harboring life. Life on Titan? It may in fact already exist. If it does, what would it look like? The search is on for the answer. Trinidad and Tobago form an island country in the southern Caribbean. They have a population of about 1.3 million. They also have one of the most unusual lakes in the world. It's called Pitch Lake. It contains not water, but naturally occurring asphalt. It bubbles up from an oil field that lies underneath, creating a lake of asphalt that's 40 hectares in area and 80 meters deep. Strangely enough, Pitch Lake is the site of fieldwork being done by astrobiologist Dirk Schultz-McCook. He thinks that Titan is the best candidate for the location of extraterrestrial life. He's come here to try to envision what life forms on Titan might be like. Asphalt, like methane, is a hydrocarbon comprised entirely of carbon and hydrogen. You wouldn't think this was a substance that harbors life, but Schultz-McCook says it actually does contain microorganisms.
Well, this is one of the few environments where it's similar to Saturn's moon Titan, where we know that we have hydrocarbon lakes on the surface. Obviously, Titan is very cold, so it's still different than from over here. But we do have the liquid methane and ethane, which are also hydrocarbons. And if we can find out what kind of organisms are living here in the asphalt lake and how they adapt to living in the hydrocarbons, we think we can get some ideas to how life could operate on a moon like Titan.
Asphalt contains almost no water.
Did you say that there's microbes in there?
Yes, there's microbial organisms in that liquid asphalt.
In this thing?
In this thing, yeah.
Like maybe 1, 2?
Millions.
Millions?
Yeah.
Genetic analysis identified some 600 new types of microorganisms living in the asphalt. Most are archaebacteria, related to the primordial microorganisms that live in extreme environments.
So for them, actually, it's a great environment, it's a great food source, and basically a never running out food source because it's getting supplied from deep down there.
On Earth, there are microorganisms that can use asphalt for sustenance instead of water. Schultz-McCook is convinced that in Titan's lakes, there must be life forms that exploit methane in a similar way. Another scientist, Chris McKay, holds that the methane lakes on Titan contain creatures so unlike Earth creatures that they exceed our wildest imaginations.
Think of fish living in water and ask them to imagine a bird which lives in air. They probably can't conceive of an organism that is so much denser than the medium in which it lives. Fish move through water by floating. So they would imagine a bird must float in the air.
We humans live in an environment called Earth. We produce energy by causing oxygen and organic matter to interact. That is our lifestyle. But McKay is arguing that on Titan, life forms would be based on a Titan lifestyle that makes use of what's available on Titan. Titan's atmosphere contains minuscule amounts of hydrogen and acetylene. McKay thinks that there may be life forms on Titan that exist by deriving energy from the interaction of those two substances in a methane environment. McKay says that life could very well already exist on Titan.
So instead of being small and round, I would guess that a single-celled organism on Titan might be big and flat, like a sheet of paper, to maximize its contact with the nutrients in this thin soup. So it's living in an environment where there's not a lot of food. So it's got to access the food with a big area, and maybe on this area it has active molecules. So it's like a big flat sheet of paper with little traps on it to collect food. To that life form, that will be the normal environment.
It was not until the 21st century that Titan's thick veil was lifted. Now that we're getting a closer look, what new discoveries await?
So Titan gives us a whole new set of possibilities, and there are for sure perhaps hundreds, maybe millions of worlds like Titan around other stars. Do those have life? Titan maybe can give us some clues.
If life is found on Titan, humanity's view of the universe will surely change.
The best place for me in terms of finding another type of life would be Titan. Because if we find it on Titan, then we know that it really is too. It's not the same as us. When we go to Mars, we may find life on Mars, but we won't be sure that it's not the same life as Earth. So my best hope would be we find life on Titan, because then I know that we found two completely different types of life. Then I can go on to some other science problem.
There is only one body in space that we know of, other than Earth, that has a thick atmosphere and lakes. Titan. If life is found on Titan, it will instantly increase the possibility that life exists in many other places in the universe as well. We may not be alone in the universe. We may have many comrades. The quest to find out for sure continues. Clues to solving that great mystery lie hidden on Titan.
you.